Hello, in this video series, we want to explore the margin of error formula found in your book and learn a little bit more about it. So it's basically just stated. We want to understand a little bit more about why it works. So let us explore. Okay, let us assume that we wanted to flip a coin. That's our standard binomial distribution. And we know that we could flip it an infinite number of times. And we know that we're likely 50% likely to get a heads on every flip. And so we would expect that half of the outcome would be heads and half of the outcomes would be tails. Let's consider a heads as being a success. Now, if we were to only flip the coin 5 times, we're going to approximate this in MATLAB. This is just a standard binomial distribution of what is likely to happen in red. Okay, so this was not a Monte Carlo simulation where we randomly did toss a coin. This is just the binomial distribution of what is likely to happen. So we can see we'll never get 2.5 heads. You will get either 0, 1, 2, 3, 4, 5, or 6 heads. I'm sorry, you will never get 6 heads, which is why you don't see anything out there. It's most likely that you would get 2 or 3 heads. So on average, you will get 2.5 heads. That's where the midline of this would be, and where the peak of the normal curve approximating this binomial distribution is. But we can see how that spreads out. Okay, so while we're expecting to get 2 or 3 heads, there's an uncertainty in how the data would actually spread out. Okay, now let's turn the story around. Let's assume we're trying to figure out whether we have a fair coin or not, one that should give us 50%. All right, it's likely that we would end up with 4 heads and 1 tail, and you might be tempted to think you don't have a fair coin. So when we flip a coin 5 times, we'll get a certain number of heads, but we should put a margin of error, an uncertainty in how many heads we really should get to mirror what would happen if we flip this, say, 5 million times, all right? So the proportion that we get by taking a sample of all of the possible flips, there could be an infinite number of flips of coins. We're only taking a sample of 5 of those flips. And it's likely that we'll get there's a great uncertainty in what the total population looks like of coin flips based on the 5 that we chose. Now, if we increase that to 10, okay, we can see, well, it becomes a little more predictable. It's not obvious yet, but it becomes fairly unlikely in terms of proportions that I'll get anything other than a 4, 5, or 6. So we're tending towards the middle of 10, which would be 5, as we have more flips. All right, and if I double that to 20, we can see that we're very, very likely to probably be somewhere between about 8 and 12. If you went down to 7 to 13, you would include all of the most likely things. It's not very likely to, and you can see looking at the bar graphs, it's very unlikely to get fewer than 5 heads, and also very unlikely to get more than 15 of them. So the answers are concentrating a little bit more towards the middle of that, given that we have a 50% probability. If we went from 20 to 40, we'll see that the curve, the histogram being approximated by a normal curve is getting narrower and narrower. We talked about the point of inflection. The point of inflection is getting closer and closer. It's about where the arrow is here, where it stops curving more and more downward. It's the steepest point in here. It stops getting steeper and steeper and starts to curve the other way, right about in here. Okay, so if I keep going up, you'll see that point of inflection moving closer and closer. Whoops, it should be an 80, closer and closer to where the middle of the data is. Okay, the middle of the probability curve. So when I went to 80, it pinched in further. If I go up to 160, I think that's about as high as I can go with this histogram. Let's see. Okay. Yes, we can see it. The spike gets narrower and narrower. So remember when we were looking at 5, it's fairly likely that we could get a number like 4. Okay, it's not even that unlikely to get 5 heads in a row, and it's if you did it enough times, you might expect that it would happen. All right, so the data could spread out a lot. So flipping a coin 5 times doesn't tell me much about what happens for all coin flips. Whereas if I do this 160 times, we're going to plot it again, we can see we would expect around 80 is the most likely event, and we would expect to certainly not get, it'd be very unlikely to get more than 90 heads, and it would be certainly less, very unlikely to get less than 70 heads. So proportionately, the data is pinching inward. And so we know more and more about the way that coins flip if we do it more times, all right? Now, this isn't a very useful thing because we kind of know what coins are supposed to do, but let's say we were trying to figure out how many people vote a certain way, okay? So we wanted to know the percentage of people who would vote Republican in the state of New Jersey. If we just select 7 people, we might find there were 4 Republicans in the bunch. We might find there were only 2. There's a lot of uncertainty in what the data would tell us about the number of Republicans in New Jersey. If, on the other hand, I sampled at random, we learned about that in the last section, say 70,000 people, that's still a small percentage of the 9 million people who live in New Jersey, but we would probably have a pretty good idea of what percentage of people are Republicans and which percentage are not. So we could, by increasing the number in our sample, we would know more and more from the sample about the population at large. Okay, so what does that qualitatively show us? Your formula had a square root of n in the denominator. So what we can qualitatively see is that n gets larger and larger. The data gets closer and closer to, in terms of proportions, to the average value, all right? So the data pinches in towards an average. It's more and more likely that the coin tosses represent what happens for the set of all possible coin tosses. Or in the case of selecting voters, our poll of voters is more likely to reflect on what the population of New Jersey is actually like. So now let's continue to look at the formula. So we know why there's an n in the denominator. We don't know why it's a square root of n, but we understand why there's an n in the denominator. Now there's a very strange thing in the numerator, a number 1.96. That seems pretty random. So let's consider what that means. So let's recall that for a data set, when we have larger data sets, it's convenient to use the normal distribution curve to approximate any binomial distribution. And here is the normal distribution curve, that is the standard one, where the standard deviation is 1 and it's centered on 0. So the average value is 0 and the standard deviation is 1, right? Now, if you look at this, I have a lower limit of -1 and an upper limit of 1. So we shaded the area in underneath of the bell curve from -1 to 1. And we can see that about 68.3% of the data is included from -1 to 1. We've talked about that in the past. Now, if I make that -2 to 2, let's look at what happens. Now we've included 95.4% of the data. And you might recall that the formula for margin of error was the formula for a 95% confidence in the margin of error. So that was in smaller print. So you can see that 2 standard deviations, if you take from to the left and the right of the mean, includes just over 95% of the data. Well, how many standard deviations should we go out to include exactly 95% of the data? Right? Well, it turns out, and we won't go exactly, but when we went from -1 to 1, we definitely didn't have 95% of the data. when we go from -2 to 2 standard deviations, we are very, very close to 95%. So what happens if we go from -1.96 up to 1.96 underneath of our normal distribution curve? The probability of being between -1.96 standard deviations and 1.96 standard deviations is in fact very, very close to 95%. Okay, so rounding off, we get 95% when we go from -1.96 standard deviations up to 1.96 standard deviations. So if I'm going to give an uncertainty in a value based on a sample of data, if I include numbers that are 1.96 standard deviations above and 1.96 standard deviations below the mean, I would probably I'll capture 95% of the data. All right, so that's where the number 1.96 comes from in the formula. Now the book gives you the margin of error formula that looks like this line of code in MATLAB. D equals 1.96 divided by 2 times the square root of n all in the denominator. Perhaps if I wrote it in MATLAB as 2 times the square root of n in parentheses. You need the parentheses around the 2 and the end in order to make sure that's all in the denominator. It will make more sense, all right? So let's run this code and see what happens. So first of all, we have 100 attempts at something that has a 50% chance of success. This looks like a coin toss, all right? So if I use the formula for D and plot as a proportion what D is out of the proportion, the number of tries, and I go from the middle, the average minus D, up to the average plus D, I will in fact include 95% of the area. So the formula seems to work. Now let's see if this works. Let's see what that means when we have different size n's. So let's start with n equal 5 again. Right? So when n equals 5, whoops, if I run this code, we can see we have a very wide bell curve, because when we toss a coin 5 times, a lot of different outcomes would be likely. Okay, so we have a very wide bell curve. So if I look at the proportionally where negative D is and we're around the mean, so the mean is right at 0.5. So if we go from negative, the mean minus D to the mean plus D, D has to be a large number, like 0.438. And that looks like a small number, but it's a large proportion. All right, D is 43.8%. So if I told you that it's 30% likely to rain tomorrow with a 43.8% error in that percentage, you'd have no idea whether it was going to rain or not. So tossing a coin 5 times gives us very little information about what, how many heads we actually ought to get if we were to do this forever, okay? Looking at the total number of possible coin tosses. Likewise, if we sample 5 people out of the population to find political affiliation, sampling 5 people gives us great uncertainty. Now, if we take that up to 10, the D as a proportion is going to be smaller. You can see that that's not going all the way out to the edges this time. Okay, so using the formula from the book, the D value jumps down to about 31%. It's a lot better. It's still pretty terrible. Okay, so let's make n equal to 20. We can see D is pinching in towards the mean. And as a percentage, we're down to a 21.9% margin of error. Make this 40. And imagine it wouldn't be that hard to toss a coin 40 times or to sample 40 people about their political affiliation. We're down to a 15.5% error. Let's just jump right to 160. We can see that the margin of error is coming down. It's all the way down to 7.75%. Now, what if that was 1,600? That would be annoying as a number of coin tosses if you had to do it by yourself. Probably want to generate that on a computer. But if you wanted to actually do a political poll of New Jersey, you probably should call 1,600 people, because if you did, your margin of error is down to under 2%. Okay, so about 2.5%. Right? If you wanted the margin of error to be even smaller, as you can see in some of the sample problems, you need to up the number of samples you have. If I multiply this by 4, that'll be 40, and that'll be 6,400. I'll cut that margin of error in half. Okay, so you can see now we're down to 1.25%. So every time you take a sample size that's 4 times larger, you half the margin of error, because there's that square root of n in the denominator. All right, so that seems pretty good. Now that's great for coin tosses, but what about political affiliation? If we were to actually look at Republicans in New Jersey, it's probably a number more like 40%, which is why election after election in presidential elections, New Jersey ends up voting for the Democratic candidate, because it's probably about 40% Republican. So if I run this now, okay, a key is, are we going to get 95% of the data included? Okay, you can actually see in that last example, we didn't quite get 95%. I think that's because my, I probably need a larger spacing. I need to use more data points. I only used 801. So as the sample size gets really large, there's a little bit of error because I didn't use larger numbers in the computer code. It'd be easy enough to do that because the computer can compute quickly. In fact, shading in the purple is what's taking all of the time, but I wanted to show you that. So this says 0.94%, but that's really should be 95% if we used higher resolution. Okay, the key is it's very close to 94%. Now, if the probability of picking a Republican isn't 50-50, what if it's really 40%? Okay. It skews the number slightly. It's hard to tell looking at this number. Let me go back down to a sample size of 100 and see what happens. Okay, you can see it's a little bit large. Now, 40% isn't that far off of 50%. Let's consider like the percentage of independents if you were going to do a poll. Let's say that 10% of people in New Jersey are independent when it comes to their political affiliation. And if you were to sample 100 people, we'd expect about 10 independents. Suddenly, this probability, you can see the purple filled in what looks to be almost all of the area under the curve. And in fact, if you look at the title, the probability has grown to 99.9% of the population. So the formula in the book doesn't work as a 95% confidence interval if the probability isn't 50%. Although you can see that the margin of error that you would have, which is 9.8% right now in this example, actually would include 99.99% of the data. So we're actually more than 99% certain that our margin of error would include the right number. Okay, but that might be more certain than we want. Okay, because our margin of error is 9.8%. It turns out, and we'll be able to derive the formula in a better way, if we really wanted to do a 95% confidence, have 95% confidence in our margin of error, that our D value shouldn't use the book formula. The D value should actually be what I have here, 1.96 times the standard deviation, all right? Because we've seen that 1.96 standard deviations from to the left and right of the mean should include 95% of the data, but we need to make it as a proportion of the population. So if we take that and divide by n, that should give us the right number. Now, what I'm going to show you in a minute is that the two formulas coincide when there's a 50-50 chance, all right? And the formula in the book is kind of a conservative formula in that it will be at least 95% accurate. So you would rather be have a margin of error that's too large than a margin of error that's too small. So where the formula isn't bad to use if you're just trying to get a rough sense of what your margin of error should be, but this formula is better. Let me run the code again. And you can see now, once again, we're very close to having 95% of the data by using 1.96 standard deviations divided by n. So the final thing I want to do is show how this formula right here actually gives the book formula. Okay, so here's our formula. That funny little looking O is really the Greek letter sigma. So the margin of error as a proportion is given by this formula. Now, what you don't know, which isn't obvious, if I wanted to find, this is something you'll learn later in statistics, if I wanted to find the mean, we put X with a bar over it, I can simply take the number of things in the sample times the probability of success, which makes sense. If it's a coin toss, P is 50%. If N is 100 and P is 0.50, you would expect that on average, you will end up with 50 heads, all right? If you were shooting basketballs and you have a 70% free throw percentage, then you would expect to make 70 shots on average. Or if you took 10 shots, you would expect on average to make 7. So that makes sense. What is beyond us right now is that the standard deviation is the square root of n times p times q, where p is the probability of success and q is the probability of success, and q is the probability of failure. So that's 1 minus p. It's the probability of failure. Okay, now that don't read too much into failure. That just simply means that if heads is a success, tails is a failure, right? So if I look at that formula, when P equals 50%, oh, so let's put this all together. So D should equal 1.96 times sigma. So the square root of n times p times q. All right, and then we divide by n. Well, this could be simplified. We have a square root of n in the numerator and a square root of p and q. So let me leave the square root of p and q up there. But when we take the square root of n and divide by n, we end up with the square root of n in the denominator. Now let's look at the case of a 50% chance for p. If p equals 50%, then the square root of p times q is equal to the square root of, let's do it as 1/2 times 1/2. And the square root of 1/2 times 1/2 is 1/2. All right, so if you recall, the formula the book just gave us was, whoops, I'm sorry about that, D is equal to 1.96. You could write that as times 1/2 over the square root of n, but rather than have 1/2 in the numerator, we could write that's 1.96 over 2 square root of n. Okay, so it turned out the 50-50 chance is the most conservative margin of error that we can use. So it's probably best, if you don't know better or don't know otherwise anything about the population, assume that the thing you're testing has a 50-50% chance of happening, and therefore the margin of error can be given conservatively by this formula. If, on the other hand, you do actually know the standard deviation of your sample, then you could say you don't actually know the standard deviation of the population, but if your sample is large enough, you could use that and take 1.96 times the standard deviation that you do have, and simply divide that by n, the square root of n. So if you can actually measure the standard deviation from your data set, if it's big enough for that to be meaningful, then go ahead and use 1.96 times sigma divided by the square root of n. But you can also use the book formula because it's faster And if the probability is near 50-50, it works very nicely. If the probability isn't near 50-50, the margin of error it gives you is a little bit too big. So it actually captures um, more data than you would think. So you're actually being extra conservative by using the formula from the book. Okay, so make sure you study your examples in the book and go ahead and do those problems.